Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We were discussing some of the applications of stable water isotopes in our previous lecture, and in this particular lecture also we are going to discuss some of the applications of δ11O in different ways. The first application that we are going to discuss, as we have started in our previous lecture as well, is how to do source apportionment So, I was explaining that δ18O and δD values, they are called conservative traces. Okay? So, these are called conservative traces. That means, when we are mixing different sources that has different δ18O and δD values, then the mixed product will have a value that is coming just from the fractional contributions of the two end members and not due to any other physical, chemical or biological interaction. Okay. In this conservative tracer mixing, even if there is slight slight changes due to physical processes, then we believe that we will be able to capture that through some kind of assumption, like if there is evapotranspiration happening, then I can use some kind of evapotranspiration factor to convert whatever amount or something and get a weighted average or some kind of calculation that would help me account for that physical process, but will no way impact the stable water isotopes from being considered as conservative. The main important factor is that they are chemically and biologically not interacting. Okay? They are not interacting. Okay? And that is very true for low temperatures. At low temperatures means something between something which is at the earth's surface. So, something around 15 to 25 degrees Celsius, we consider this is true. So, there is no chemical interaction, no biological interaction, and even if that is, the water composition is not going to change. That means, if I am collecting a river water sample, no solute interaction is going to change my δ18O and δD values. Okay. Similarly, biological interactions are also not going to change my δ18O and δD values of the water. Okay. They themselves can get changed if there is any kind of precipitation happening in carbonate shells and all that, they might get changed because they are precipitating from the water, but my water will not change. My sample water, which is like a river water or a lake water or a groundwater, that is not changing. So, my water remains constant. So, that is what I mean by conservative. That means they are not going to change with any kind of interaction. What is the other end of the this kind of tracer? It is called non-conservative traces. Okay. What are non-conservative traces? Non-conservative traces are something like solutes, like alkali elements and transition metals and all that. So, any kind of solutes, for instance like sodium, okay. Sodium which is coming from different end members can also in the river get changed due to weathering, right, because weathering is an activity that is happening in the river itself. So, that kind of interaction with the sediments, more weathering, intense weathering, whatever chemical interactions is happening, sodium is susceptible to it. Plus, it is also susceptible to the biotic uptake and release. Okay. So, therefore, the solutes are my non-conservative traces as compared to my water isotopes, which are conservative isotopes because they are chemically and biologically inert. It means no kind of uptake or anything, no kind of interaction is going to change my water isotope composition. Okay. So, therefore, they are extremely well, they work extremely well in this kind of source apportionment application. And here is an example. Now, when we have when we have multiple source n members, so what happens is when we have n members, the rule is that if we have x number of n members, then we need at least x minus 1 traces. Remember this, if we have x number of n members, then we need at least x minus 1 traces. That means, if my n members are 4 n members, I need at least 3 traces, 3 distinct traces. If I have at least 3 n members, then I need at least 2 traces. Then I need at least 2 traces. So, the number of n members you have, potential n members, you will decide how many traces you will be able to apply. So, that is one thing. Now, another important factor is that we cannot use both delta 18O and delta D simultaneously. Why? Because they are interdependent on each other, they are not independent of each other, they are rather interdependent on each other. That means, my delta 18O value and my delta D value is linked, right? It is linked, it's having a correlation. So, it is very well correlated. So, as you can see. So, when I am doing any kind of source apportionment, I cannot use them as independent traces. I can use any one of them. I can either use delta 18O or I can use delta D. So, either one of them I will be able to use, but both of them I cannot use as independent traces. So, there is a possibility of finding another third tracer. Okay. So, if I need at least 2 traces, I will use delta 18O and I have to use something else. Now, often at times we have seen that we use some kind of pseudo conservative traces. What are pseudo conservative traces? They are something like chloride or electrical conductivity, where we see that they are not very chemically or biologically active. Okay. And that is mostly mostly true if the distance through which we are applying it is a small distance. If the system is the system where we are applying it is huge, then we cannot use any kind of pseudo conservative traces. Only for short distances we can use it as a pseudo conservative traces, because we know that over the short distance it behaves almost like a closed system. There is not a lot of interactions over the small system. But if you are considering it as a huge lake or a very long river, it cannot be done. Maybe a few 50 kilometers or down to 100 kilometer maximum, you can consider that it behaves like a pseudo conservative tracer. For instance, here you see that they are trying to trace the mixing of the mixing that is happening in groundwater from different sources. So, one thing is the local Missouri groundwaters, then there is the exotic waters from Rocky Mountains with low delta D values, and there is another which is brine. Okay. So, there are brines. Okay. So, there are 3 distinct waters. So, one thing is this original Missouri groundwaters, then there is some kind of brine solution, and there is some other high altitude very low mountain water, very low delta 18O enriched and delta D enriched mountain waters. So, high altitude waters, and they are mixing, and they also have very distinct chloride values. So, the brines, they always have very high salinities. The Colorado water, they also have moderate salinity, but this local Missouri groundwater will have far less salinity, right. So, this is our mixing model. We have at least two sources, that is the brines and the local Missouri groundwaters and the Colorado. So, there are 3 sources and we have 2 traces, right. We have 2 traces, either we use the delta 18O or and we use the chloride, or we use the delta D and we use the chloride, and then try to solve this kind of equations where we write delta 18O of the groundwater, okay, of the groundwater that we are trying to understand is equal to the fractional contributions from Colorado water into this delta value of Colorado water plus the fraction of brine into delta value of brine plus the fractional contribution from local this local Missouri groundwater into the delta 18O value of the local Missouri groundwater. So, this is my equation. So, write that I am going to write for my chloride also. Okay. So, like that I will write my chloride equation also, that is my chloride mix, and I will write the final equation, that is fractional contribution from Colorado water plus the fractional contribution from brines plus the fractional contribution from the local Missouri groundwater is all equal to 1 or 100%. Okay. So, this is my 3 equations that I am going to solve. Okay. These are my 3 equations that I am going to solve for my end member calculations. Okay. Now, what happens is if we do not have very very good control of our pseudo conservative tracer for something like electrical conductivity or chloride, then we may have to depend on another way to utilize delta 18O and delta D values, and that comes from this term called deuterium excess. Right. We used this, we will use this parameter because this D excess value now is independent of delta 18O. There is no delta 18O and D excess correlation. Okay. There is no delta 18O and D excess correlation. We only find it with delta D, but whatever is the intercept value, if you have that, so what you can do is you can first find what is the local meteoric water line, or if you are using the river, then what is the river meteoric water line. So, first find the D excess values, and then using the D excess values we can use the D excess as an independent tracer from the delta 18O. It is separate from the delta 18O. The delta 18O and the D excess do not have any correlation. And here is a mixing model that I have used some time ago for finding the contributions in river during the different seasons. Okay, so, this is the pre-monsoon, this is during the monsoon, and this is during the post-monsoon. And what other things I also included is that we often see that for any kind of end member, for instance, if we have groundwater as an end member, if we have mountain some kind of ice melt water or snow melt water, or even if if you are using brines, depending on whatever is the end member, they can have a natural distribution, like a natural variation. For instance, you see that the brine has a variation in this region. Okay, this is the region. So, somewhere between 2 and 3, and here in this axis somewhere between maybe -5 to -7, 8. So, like that kind of variation is there, and often it may happen that if you use a particular value, weighted value, okay, you select that okay, I am going to use this value, okay, or I am going to use a weighted value or something, some other value, okay, you single pick one value from this box, then often it may happen that that result that you generate becomes very sensitive to this value that you have selected. I mean, if you are changing this value, you take another value next day, you use this value, your answer will be different. Okay. So, this is called a sensitivity analysis, that is, by selecting different end member compositions, you see how your results are varying, okay, and whether it is justifiable to consider a single value for your end member. Okay. So, considering both these both these parameters, both these factors, rather what you can do is you can give a small range such that you know that your maximum variability will happen in that range. So, here is a particular example. Okay. So, here the gray, there is a gray box, there is a blue box and there is a pink region, okay, and that shows these end members. So, these are the 3 end members A, B and C. Same thing, A, B, C, A, B, C. Okay. These are my end members, okay, and they are, the gray is the glacier end member, B is the precipitation end member and C is my groundwater end member. Okay. And these are their compositional fields, that means my data of groundwater will lie within this blue box, my data of groundwater will lie within this blue color box in the monsoon, it will lie fall like this again in the post monsoon. So, when I am doing such kind of modeling, I am slowly trying to develop more probabilistic modeling as compared to deterministic modeling. In deterministic modeling, I am going to choose a single value from my end member composition. What I am doing, I am choosing a single value for my end member composition, only one value. So, that is called deterministic approach. This type of modeling, where I give ranges for every end member, is more called probabilistic approach. It is a more probabilistic approach, right. So, probably my end member data is always lying within this box. Okay. And now, when I am doing my calculations, I am selecting values randomly from this area. So, what I am doing now is I am using a probabilistic distribution to be included in a kind of simulation model. Okay. So, for instance, I will simulate this calculation for every sample, for every data point, maybe 10,000 times or 50,000 times or 100,000 times, and each and every time a random generator will be, a random distribution will pick up these end member compositions from these boxes, and then I am going to do this calculation. So, do you understand the difference between deterministic and probabilistic? In deterministic, we are fixed with the end member composition. Every time I do the calculation, it is only once, done only once and with a single value of that end member. In a probabilistic approach, I am giving a natural range of natural variability. I know that every water has a certain range of natural variations, and I do not have a very confidence to give in to a weighted average value. Therefore, what will I do? I will use a range. I will use a range of values, and I will use a simulative calculation. So, I will calculate, this is more this is more of a Monte Carlo model, where I am picking up end member values randomly from these boxes for many times. So, for every point I have either 10,000 runs or 50,000 runs or 100,000 runs. So, 100,000 times this calculation is being done for one result generation. Okay. It can be a very time taking process, but what happens is then you get a more robust data. That means your values will not change whether you selected this as your n member composition or this as your n member composition. It no longer depends on that. Your values are so averaged, it is very robust. Okay. So, this is another type of doing mixing models, and what we do call this black line is we call it as a mixing space. We call it as a mixing space. Now, what will happen? Sometimes some values will fall outside my mixing space. What to do at that time? What will I do at that time? So, either I have to shift my n member compositions accordingly. My n member compositions would have to shift if I see that my values are lying outside this box, that I know, then I know that okay, this needs some kind of shifting of the boxes. Also, I will try to prevent overlapping of different m members as much as possible. Okay, as much as possible, you are trying to prevent overlapping signatures. Okay. So, this is the best way where you have three different n members which is completely separate. Their compositional spaces are very different as compared to here in this last figure, where you have some data which is falling outside of the mixing space, because for these data points you will get no results. You will not be able to generate results, because this is outside your mixing space. You will not be able to converge the model, you will not be able to get the results. So, what you can do is you have to either move your boxes, okay, and you will be able to increase this mixing space such that now you are able to generate some results. Okay. Also, try to prevent such overlapping. Also, try to prevent such overlapping of n member compositions. Now, that is with coming to an end with the mixing model. Now, let us see why some glacial ice compositions look the way that they do. Now, what application that we understand of stable water isotopes in the in the glaciology field. Now, glaciers, they are being formed at very high latitudes, very high altitudes. So, therefore, naturally we expect that they are going to be isotopically very light, right. That is, when the water is evaporating from the ocean, all the H2O, which is like H and this is oxygen is in the 16 form, first they are going to get evaporated and they are going to form get precipitated over the land. Now, during non-glaciated times, what happens is that this precipitation also comes back through runoff, rivers, groundwater discharge back to the ocean. So, the hydrological cycle gets completed. But during glaciated times meaning time periods on Earth's time scale, where there is formation of ice, where there is formation of glaciers, and we are in a very cold temperature. So, Earth's temperature is always in between a glacier and an interglacial cycle. We are either in a glacial cycle or we are in an interglacial cycle. Okay. So, right now present day, that is 2025, we are in an interglacial period. That means our temperatures are rising, our glaciers are melting. So, we are that kind of situation, but it has not always been like this. In the past, we have had colder temperatures where the glaciers were being formed, where the temperatures were far colder, some 10-15,000 years back ago, and this kind of cycle of glaciation and interglaciation, glaciation and interglaciation is related to the Milankovitch cycles and therefore has a cyclical effect, and it has always happened over the billions of years in Earth's history. So, what has this led to? So, this has led to some strong isotope fractionation that we have seen in the in the periods where we have ice and when the periods with that we do not have ice. So, during the glaciation period, the 16 oxygen gets trapped in the ice. It is always getting trapped, okay. It is not returning back as runoff or as groundwater or through the rivers. It is not no more coming back to the ocean. So, the ocean is getting more and more 18 oxygen enriched and 16 oxygen depleted. So, during the glaciation time, the sea level is gradually dropping because the water is getting now stored in the form of ice over the land mass, either over the land mass if it is in the continental glaciers, or it can be in the Antarctic, which is like polar ice mass. Okay. So, Arctic, Antarctic, large areas of huge ice masses, or over the continental glaciers, something like the Himalayas, in the Europe, in the North America you have the Rocky Mountains. So, the Canadian glaciers, the Russian northern Arctic circle, there you have lot of other continental glaciers. So, those glaciers are locking the water. So, they are trapping all the 16 oxygen and they are not releasing it back to the ocean. So, during glaciations, the 18 oxygen by 16 oxygen ratio of sea water increases, and during the interglaciation time, during the melting season, during the melt, the long time scale of interglaciation, something that is currently happening, these melt water returns back to the ocean. So, now my 16 oxygen returns back to the ocean. Therefore, the 18 oxygen by 16 oxygen ratio of the sea water falls down during the interglaciation period. And this helps us in understanding what kind of temperature Earth has had in its past. So, here is a plot, the first plot is showing the variation of delta 18O in sea water during the glaciation and interglaciation cycle for the past 2 million years, over the past 2 million years. So, the higher the 18 oxygen by 16 oxygen ratio means, the higher 18 oxygen and the 16 oxygen means we are going towards a more glaciated glacier formation. So, we are going towards more colder temperatures. A lower 18 oxygen by 16 oxygen in the ocean means that the runoff is bringing in all the ice melt water, and that means we are in a interglaciation period. So, these kind of fluctuations where you see like a sawtooth pattern. So, once glaciation, once interglaciation, again one glaciation, again one interglaciation, again one glaciation, again one interglaciation. So, such kind of sawtooth pattern is always observed, and it just follows the Earth's Milankovitch cycles. So, this kind of 18 oxygen data is extremely helpful to help us understand how Earth's history, the temperatures has changed, and at what time periods do we see these fluctuations. How many years ago, at what time scale did the temperature again fall, what is the cyclical length. Okay. For instance, this is for sea water. Just the opposite is expected in ice core. Now, in the ice core, during the glaciation period, the delta 18O value will be very low, right. It is getting more and more enriched in 16 oxygen and more depleted in 18 oxygen. So, during the more glaciation period, the values will be more and more negative as compared to the interglaciation period, where the values are more and more positive. So, this is from ice core data. This ice core is from from a core which is called Camp Century, taken from Greenland, And this is one of the best recorded core, because it's extremely difficult to core an ice sheet and take it out as a piece, like to take it out a whole, it gets broken, it's difficult to get retract. So, with all the challenges that people, scientists, glaciologists specifically, that they face, this is one of the longest cores ever retracted, which is almost like 1373 meters. Just imagine, more than a kilometer length of glacial ice core, and this has been dated for, so if you are using different methods of dating, this has been dated correctly for around 126,000 years, and we have marked all the boundaries. So, all the Holocene boundary, all the Wisconsin so all the different era and time period boundaries has been marked, and based on that, now we superimpose the 18 oxygen data, and we see, okay, how the 18 oxygen isotopes show us periods of glaciation versus periods of interglaciation or warmer time periods. And during warmer time periods, the sea levels will rise, and these are called the high sea level stands. That means there are immense increase in the sea level, and during this period, which is broken down into Barbados 1, Barbados 2, Barbados 3, there is a lot of progression of the ocean masses of the sea into the continents. So, during this period, a major part of the coastal areas would have been inside the sea as compared to what we find today. Okay, so these are one of the highest sea level stands that we call them, and they therefore show highest delta 18O values measured in the entire section. So, these are basically warm periods, okay, warm periods. Therefore, the ice value shows more positive temperature as compared to cold temperatures, where this is the last glacial maximum. Okay. So, this is the last glacial maximum when the Himalaya was expanded hugely. All other continental glaciers were in its full form. So, that was the last glacial maximum at around 18 or so, something between 10 to 18,000 years ago. So, something around 10, after 10 to 18,000 years ago, we had this huge what we call the last ice age. So, therefore, delta 18O is used as a paleo-temperature proxy, because this kind of change in the data set of 18 oxygen helps us understand what kind of temperature would have been present at that time on Earth's planet, and would help us understand how the temperature has varied over the Earth's past history. Now, we not only check delta 18O values from water, we also try to use other proxies. And what are those other proxies? It is carbonates, right, because these carbonates, they are precipitating from the ocean itself. Okay. So, when it is precipitating from the ocean, it is in isotopic equilibrium with the water. So, something precipitating out of the water is in equilibrium with the water at that particular time. So, when their shells and when the exoskeletons are forming, at that time, whatever the water composition was, it is recording that. Okay. It is recording with its ambient water isotope composition. So, since this delta 18O composition that we can get back from this species, exoskeleton or some skeletons or shells mostly, then I am going to able to get that delta 18O value and correlate with it the temperature. So, this kind of study is called paleo-temperature studies, and there are many, it is an entire branch of study, several proxies has been very useful to correctly determine the past temperatures. And it is not that all animals are going to record it. So, there are many biological factors related to the complexity of the animal, related to the metabolic activities, external factors such as if there is any other chemistry is changing rapidly of the water and all that. So, depending on that, how sensitive is that animal to such changes. So, depending on a lot of factors, there can be a biological effect. We have found out through trial and error methods that only certain species of animals can be very good proxies, and among them are these deep sea forams. So, these are tiny animals whose exoskeleton, whose shells we are going to use as our proxy for paleo-temperature. So, these tiny forams, these are microscopic animals. Their shells are precipitated with equilibrium with the ocean water, and as they get deposited in the ocean sediments, okay, as they die and their shells get deposited in the ocean sediments, we take out the ocean cores. Okay, we will take out ocean core, a sedimental core, and from the cores we are going to the cores are, there are various ways of dating those cores. Depending on the dating of the cores, depending on the sedimentation rate, all of that, we are going to first date the shells. Okay, the shells from each each area of the core. So, if this is a core, you are going to divide it into equal time periods, and you are going to, so the forams will be there at each and every interval, and at every interval you are going to pick up these forams and you are going to do this analysis, and you are going to see okay, how this is varying. So, this is varying, that means okay, there is a shift between the glacier and the interglacial period. How did it vary? So, we need evidences from multiple proxies when we are putting forward hypothesis, when we are testing Earth's history, when we need multiple proxies. And there is something called the ice volume effect. That means there is a slight shift which is of course corrected, when we are recording the δ11O from marine carbonates that grew during interglacial and glacial period. So, given this correction, we are going to use it as a paleo-temperature proxy. Okay. So, this is called the ice volume effect, that whenever there is a shift in the δ11O values, specifically in the carbonates we observe, we say there is a this is because of the ice volume. Okay. This is called the ice volume effect. So, there is a shift almost for 1.5 parts per mil, and this shift, this is a huge shift in terms of stable water isotopes, and this is mainly recorded by the carbonates due to the shift in the interglaciation and glaciation cycle. And remember that this is deep sea, this is not surface sea. I am going to talk more about this deep sea and surface sea related changes in our next lecture. For today, I am closing this lecture. Thank you.